Sorry. Yeah. Okay, does it work? Okay, good afternoon. And yeah, first I'd like to thank Maur and Wilson for having me here. It's a great pleasure again to be and to talk in front of this selected audience. Now let's switch the gear, and from this modern and fancy things we were we're hearing this morning, and the first talk of this session, let's go to something a little bit old-fashioned, but which is quite related to the way physics of vortices was starting. Basically, in the beginning of since it's sort of a little bit memorial conference, then maybe a short word of memory will be in order. So when Vortex Science was in its infantry, all the concepts from all other sciences were borrowed and used to advance our knowledge about vortices. But now it looks like our beautiful Vortex Science is so advanced that it can pay all the debts to other sciences or to other areas of physics and bring some news there. So this is what we're going to do now. And we're going to discuss dynamic vortex Mott transition. And actually this was for the first time where real dynamic Mott transition was ever observed. Okay, so let's start the story. So this is our beautiful international team, and Tatiana is here, so she will be, she can always correct me when I'm saying something completely wrong. So it's great. And so let's go to the business. So in the very beginning of Vortex Science, when pinning of vortices was discussed, following beautiful David Nelson's suggestion, or not suggestion, idea by Matthew Fisher and David Nelson that there is a duality between vortices and two-dimensional quantum particles, we came up with the hypothesis that in the special situation when the number of columnar defects in a crystal, in a sample matches the number of vortices, something like electronic Mott state should form. And at this moment, we just saw it like an inspiring suggestion which helped us to discuss vortex physics. Very soon, in the group, Katie Muller, and when Elie Zeldov was there, they really experimentally discovered this Mott phase. And then it was realized that this vortex Mott phase is going to be a perfect laboratory to observe the thing which was very difficult to observe in electronic system, I mean dynamic Mott transition. So the best experiment in this field was done by Dima, who is also here and can correct me again if necessary. And they observed indeed the dynamic electric field-driven transition in a system which is traditional for investigations of Mott physics. And what they conclude, however, was that what they see is not actually the pure Mottness, but something which is impurity-provoked avalanche-like behavior, which was a beautiful observation in itself, but it was not a real observation of the dynamic Mott transition. So this came the idea that the dynamic Mott transition can be observed in a superconducting proximity system, because it is this proximity system which basically realizes pretty well Hubbard model. You just have those are superconducting islands on the gold substrate, and vortices are trapped in between. And therefore, in the moment when we have perfect match between the number of vortices and number of the potential wells, we should have this vortex state. And since this phase is absolutely ideal, like in terms of regularity, there is no detrimental effects of disorder, and we can indeed hope to observe dynamic Mott transition. And it was observed. And well, and this is just the usual data, which most people are calling matching effect. So this is the resistance, magnetic resistance, and this is, okay, filling factor. And we can see the dips at the moment when vortex structure is commensurate with the structure of the potential well. So everything is as usual, and there are tons of observations like that. And the only thing, remarkable thing, is that if we now go and see what is differential resistance is doing at the same time, we can see that at the moment when it has strongest spinning, this differential resistance shows wonderful like flip. So from like dips down to the flips up. And this is just direct and unambiguous evidence of the Mott behavior. So we have the transition from the Mott insulator to the Mott metal, whatever it is, in the vortex system. And to verify this hypothesis, we have done the usual Mott scaling. So this is just magnified vicinity of the commensurability point. This is the separatrix. If we take out separatrix, we immediately get this fan-like structure, which is indicative to transition. Well, then the only thing to do is to scale. And this is the standard scaling. Actually, there are two of them. So Tatiana was like, okay, to do this beautiful scaling and propose this cross-check, because, well, there are two ways. This was the way of finding the scaling exponents introduced many years ago by Hebert and Palanen, and we can do independent scaling and obtain the same scaling exponents, which was good. So this was the first inspiring result. Yeah, why it was so inspiring? Because the scaling exponents which we have found appear to be exactly the same as scaling exponents for the usual thermodynamic Mott transition, but just with the interchange of temperature by current. And then it was the idea that we can move vortex system across the transition line, changing either temperature or driving current, and see if indeed in this case sort of thermodynamic behavior is equivalent to the dynamic transition. And this again was like another version of beautiful scaling again done by Tatiana, where we have seen that both thermal driven Mott transition and electric current driven Mott transition not only show the same critical exponents, but also have exactly the same scaling function. So this is, okay, those are two scaling functions for thermally driven and dynamically driven Mott transition, and those are, okay, two of them just, okay, collapsing one on top of each other. Well, okay, this I probably just, okay, skip. Okay, now the next story. So these results were so inspiring and beautiful that it seemed really unfair if they remain unexplained. But the problem was that the existing, well, that existing theories of the Mott transition didn't want to describe the collapse of the Mott's gap. And okay, actually they didn't work in the close vicinity of the transition. Basically, well, there is, okay, let's come back for the moment. So basically, there is a problem with the Mott transition in general, because usual Landau theory or Landau paradigm doesn't work in this case, because to construct Ginsburg-Landau free energy, one should have order parameter, which is averaged over the ground state. And in the case of the Mott transition, basically the Mott gap, which could serve as a natural order parameter, is in fact, okay, this is the difference between first excited and the ground state, so we cannot even construct the order parameter in case of Mott transition. This is the thing which is well known for those who are doing Mott physics, but this, what is like stumbling block for the usual thermodynamic Mott theory, appears to be a beautiful stepstone if we're trying to construct the dynamic theory of the Mott transition, because what we have to do is basically we have to calculate the probability of going from the ground to the first excited state, and this will be the rate with which Mott gap decays. So this is, okay, so this is what we should do. But if we, again, try to do it like straightforwardly, then we will immediately see that no theory can give you the collapse of the Mott gap. So the best you can get is the block oscillations, but not really decay of the Mott gap near the transition. And then it appeared that there is a new machinery, new apparatus, which is called Nonhermitian quantum mechanics, which seems to be like designed specifically for this case. What's the, well, this was, actually this Nonhermitian quantum mechanics was introduced by George Gamow in 1928, was, okay, the previous slide, when he developed his theory of beta and alpha decay. So he was not scared about non-hermiticity. And then recently it was Carl Bender who made an important step and realized that this Nonhermitian quantum mechanics is something which has the right for existence. But what was really interesting was the following. He observed that if you have a spectrum, that if you have non-Hermitian but Hamiltonian which has combined parity time reversal symmetry, then if this non-Hermicity increases, then the Hamiltonian, well, the eigenstates will lose this symmetry. Then the pairs of the states merge. And basically this is a new kind of phase transition in this non-Hermitian quantum mechanics. But okay, we can see that this behavior of the ground and the first excited state, this is exactly what we need. So if we associate our non-Hermicity with the applied electric field or applied current, then this non-Hermitian quantum mechanics immediately describes you the collapse of the Mott gap in our case. So the only thing which we have to do the thing, okay, and this is the illustration why we think that this non-Hermitian quantum mechanics, when we have PT symmetric Hamiltonian, is actually a perfect tool to describe non-equilibrium physics. Suppose that you have this, okay, pure mechanical system, okay, some like source of energy, then the pipe to transfer the energy, and then, okay, the drain. So if you reflect it, means parity symmetry, you'll have the picture like that, it's reversed. But if we make time symmetry operation, then we recover the original system. So it's just the illustration that if we have the system in which balance and loss of energy is observed, then this system should be described or can be described by the PT symmetric Hamiltonian. And this is the machinery which we are going to do and to exploit, to describe in particular Mott transition. And well, and basically just taking the description of the Mott transition as a starting point and inspiration, it happens that we're able to construct the complete theory of the phase transitions in the systems far from equilibrium. And as you well know, this theory didn't exist. Actually, there is no way of like general handling of far from equilibrium systems, and for the good reason. There is no any principle in non-equilibrium systems which would be equally powerful as the principle of the minimal energy for thermodynamic systems. And therefore, such a method of handling the systems far from equilibrium didn't exist. Now, we can probably justly claim that we sort of devised this universal method of handling non-equilibrium systems. So let's see how does it work. So to start, if we are on a just like recipe level, we're doing the thing which is absolutely incorrect and fully illegal. We take the Hamiltonian of our system and we add to the Hamiltonian of our system imaginary force, which does not exist in the reality. After that, we use this Hamiltonian to describe our system, and then, as we will see, it will immediately provide us the tool to calculate how this Mott gap indeed decays as we come closer to the Mott transition. So what we have to do is to calculate the probability of the decay of the Mott insulating state. This is done by the generalized Landau-Zinner approach. Actually, there is, okay, we can open a textbook, for example, Landau and Lifshitz quantum mechanics, and there is famous Landau-Dehne formula there. So let's take the formula from the textbook and calculate the rate of the decay of the Mott state. So the only thing which we have to do, we add imaginary potential. We'll do some like trivial calculations. Actually, this is the picture from the Landau textbook, Landau and Lifshitz textbook. The only difference is that we have this imaginary gauge potential, which reflects that our system is open dissipative system and is under the applied drive. Then we do the calculations. It's just, well, in this particular case of the vortex field, it's especially easy. So those just the action we start with, since we have a steady state, this we don't need this term. And then we have something like Schrödinger equation with the imaginary applied drive, and we immediately calculate how this Mott gap collapses, and well, and this is what we get just in a few lines. We immediately get the exponent, exactly the same exponent which appeared in the experiment. And this result actually is quite general. This result is very general for any one-dimensional system which experiences this dynamic or far from equilibrium phase transition. This exponent appeared many years ago in the famous paper by Larkin and Dovchinnikov when they were considering Josephson junction arrays. And well, most recently, probably it appeared in the beautiful, where are them? Dima's and, okay, Dima and Giannis' work on the strong pinning, where it was the same 3/2 appeared. And this is a very general thing. This is like, okay, the structure of the dynamic phase transition for a system which can be equivalently described as a one-dimensional particle. Okay, now, all this is good, but now we would like, okay, it's still not a theory of the non-equilibrium behavior. Why? Because we just, okay, did it absolutely illegally. We put imaginary term by hands. So what we would like to do is to see some justification why in the system, which is subject to the external drive, really imaginary driving potential should be generated. Well, first we have to start with some phenomenological consideration. And this phenomenological consideration actually is very simple. All is standard. We have to do just Legendre transform of our original Hamiltonian. And then we can immediately see that this Legendre multiplier is equivalent to imaginary vector potential, indeed. And when this potential is small, our eigenstates are the same as of the Hamiltonian. And when it becomes large, then our eigenstates is supposed to become complex. And this exactly means the loss of PT symmetry, because those will be eigenstates of the current. Well, then, just to make sure that everything works all right, we have to construct density matrix for such a system and see that, okay, that this phenomenological approach really works. So this is done on phenomenological level. How much time do I have? 4 minutes? Okay. 1 minute. Okay, it's enough. But now, to complete the theory, what we have to do is to really construct a microscopic derivation of this imaginary force. And this can be easily done. So what we have to do, we have to take like the standard model for superconductivity, disordered superconductor in the non-equilibrium conditions. So there are two versions. Okay, the first one was derived by Levchenko and Kamenev, and then we did some another version of this theory in which gauge transformation come explicitly, and then doing like the chain of absolutely standard transformation with this. Okay, this is Keldysh formulation of the non-equilibrium behavior of disordered superconductor. So going through the chain of absolutely formal transformations, we can end up with, okay, let me flash, okay. This is final formula. This is, again, absolutely standard formula, which could have been written in this form probably a long time ago. But we have written it in a way to make it obvious that nonhermicity is actually built in. And to make it absolutely like, okay, straightforward, we can make expansion at small fields and obtain immediately the equation of motion, which contains explicitly this imaginary potential. This is the standard equation of motion for the BCS gap. Well, now we can say that probably we indeed completed the full theory of phase transitions in far from equilibrium systems. And the only one word is why it was not done like 50 years ago or whatever. But it's always useful to read classical works. For example, if one takes the famous work by Gaikov and Eliashberg, which basically contains everything about superconductivity, non-equilibrium superconductivity one can imagine, looking at it attentively enough, one can see that this non-Hermitian term was there. They just either didn't notice or didn't find it necessary to discuss. But okay. But here we are. Thank you for your attention.